Okay, so now we are a bit changing the subject. We have been doing Newton's dynamics. We have been studying friction and rotational motion. Well, this will be an application of rotational motion in a sense. We will be studying the planetary motion, how the planets move. I will be changing a bit the order of the material in the book. In the book, the Kepler's laws is in the 5th chapter. But historically, it was first the Kepler who made his observations. Now, this is much before Newton. Now, first we had, for the history of the humanity, we always looked at the stars. How we were wondering what they were. And then we had enough materials to make measurements about their position in the sky. We could measure their position, how the position changed with time. So we had all this data about the positions of the planets as a function of time. We knew the positions with respect to Earth. Now you have this huge amount of data. If you just consider yourself at the shoes of the Kepler, just imagine you have these enormous amounts of data. You don't know what they are. You don't know if there are any relation between them. You don't know anything about how the nature behaves. So you just have these numbers which tell you where a planet is at a given time. You have thousands of points. He just made up, as one of your friends said, that is what we do in physics. You just invent things, make up things. Some of them turn out to be wrong. Most of them turn out to be wrong. Very few of them turn out to be correct. And what Kepler found out among all these thousands of data points, thousands of numbers he had, he made 3 observations. He didn't know anything about Newton's law. He didn't know anything about dynamics, by the way. He didn't have any calculus whatsoever. So first, the orbits of the planets are ellipses. This is his first observation. Well, we will discuss what an ellipse is. Second, if you take the vector, the line connecting sun to the planet, it will be going over an area in a given time. That area is independent of, as long as you observe the planet for a fixed amount of time, that area is the same, independent of when you observe your planet. Whether you start making your observation when your planet is somewhere over there, it sweeps an area, or you make another observation when your planet is over there, it sweeps another area. It might be much further away than the sun, but nevertheless, the area it will sweep will be exactly equal to the area that it swept when you started making observation when the planet was over there. And third, from all this data, the orbits and the position of the planets as a function of time, you can measure its period, the time it takes to complete one full revolution. You know the radius, the average radius, let's say this is called the semi-major axis. So if you take 2 planets, the ratio of their periods squared and the ratio of their average distance from the sun are related by this. The square of the ratio of one, the period, is equal to the cubed of the ratio of the average distances. Or if you can put it in another way, the period squared of any planet divided by the average distance from the sun of that planet, cubed, is the same for all the planets. If you calculate this for one planet, and then it's the same number for all the planets in the solar system. So these were his observations. So he had these thousands of data, numbers. From those numbers, he figured out some patterns in those numbers. So this is the patterns he observed. Until Kepler's time, by the way, it was believed that the Earth was the center of the universe. So everything was centered at Earth. So he's one of the first ones who proposed that it's not the Earth that is at the center, but if you put sun at the center, things become much more simple. And he had these laws. So what each of these laws mean? What is an ellipse? So let's just first start with the definition of an ellipse. Well, yes. Well, if you consider the circle are the points at which are equidistant from a given center. The ellipse has two focus points. Let's call them F1 and F2. And if you just attach a string to those 2 points, a loose string, you just take your pen, stretch the string, and just go around these circles, around these points as far as the string allows you. So you will end up having an ellipse. So for any points, if you take this point on the ellipse, consider this length, the sum of these two lengths. Or if you take this point on the ellipse and consider the sum of these two lengths, you will see that the sum of these two lengths is equal to the sum of the other two lengths. This is the sun over here. The sum of the distance of the planet P from the P1, the planet is at P1. The sum of the distances from the sun plus the other focal point is equal to from P2 from this, the sum of the distances of P2 from this point from the sun. The sum of these distances are the same. Personally, I have no idea how one can come up with such an information from just numbers. Even if you know the position of object, you can, I mean, you are in a time when people believe that the orbits of the planets had such weird shapes. Since the things were centered at Earth, this was the orbit of the planets, how they looked like. And Kepler, somehow, I have absolutely no idea how, I mean, this is kind of his genius. From such an orbit, he observed that if you go to another coordinate axis centered at the sun, this just becomes this one. Now, this is kind of the genius of Kepler. Okay, this is the first law, his first observation. Now, the second observation is this one. So this is, let's take an ellipse. Here, you look at a planet, and it's at this point. You follow the trajectory of the planet for some time delta t. You see that after time delta t, it will come to this point. Okay, this is the sun. So you have an area over here. Let's call it A1. And then you observe the planet that it is now here. You wait for the same amount of time, delta t. And at the end of that time, delta t, your planet is here. So there is another area over here. This is A2. These two areas are equal. A1 is equal to A2. This is his observation. This is just observation from just numbers. This is what he got. Remember, he started with orbits that look like this. From this one, he got these numbers. Well, let's see what this means. From now, we know what Newton had invented. We have the infinitesimal calculus. We have the dynamics. Now let's see what this law implies in terms of our kinematical variables. Let's just assume that this delta t is a very small amount of time. So there is no restriction on the value of this delta t. It can be, you can observe the planets for a very large amount of time or a very small amount of time. Let's just assume that it is a very small amount of time. Then I have this shape, which looks almost like a triangle. Well, this is not a straight line, but it is almost straight. This is the straight line. This is the arc. Well, this arc has length. Well, its velocity, its speed. Well, I'm making an observation for delta t seconds, or delta t unit of time. So the distance it's traveled during that time is its speed times delta t. Here I have almost a triangle. The area of this triangle, A1 Well, the base side, the length of this base side is the radius, the distance from the center, the distance from the sun. So the area is 1 over 2, the base length of that triangle, times the height. Here I have a height. Now this delta S is the length of this arc over here. So you see I have an arc over there. I have an arc over here. Well, this is a straight line. The length of this arc is almost equal to the length of this straight line over there. Furthermore, this angle here is pi minus theta. So the height of this triangle is nothing but the length of this straight line times sine of this angle over there. So height is delta S times sine of pi minus theta. Why did I define it as pi minus theta but rather than the theta? Well, it is basically because this is my position vector, the radius vector, pointing in this direction. This is my velocity vector. I define theta as the angle between the position vector and the velocity vector. So this angle over here, this angle is my theta angle. So the area of this triangle is approximately, which is exact in the limit when this delta t is very small. So area A1 is approximately equal to 1 over 2 or, well, the height is delta S, which is V delta t, times sine of pi minus theta is nothing but sine of theta. So what Kepler's second law tells me that this 1 over 2 r times v times sine theta delta t, as long as delta t is constant, it is the same independent of at which point you start making your observation. So whether you start making your observation from here and then the object moves there, or you start making your observation here and in this time delta t your object goes from here to here. Kepler's observation tells us that it is the same whether I'm here or here. Well, the difference between this point and this point is that at this point the radius gets smaller. As I go from here to here, the distance from the sun gets smaller, but the velocity increases and this theta somewhat changes. So the decrease in r and the increase in the velocity and the speed, and the change in sine theta, they are such that the product doesn't change. That is what Kepler's second law tells us. Okay, just one observation. We have r is a vector, the position vector, relative to the sun. V, it's the magnitude of the velocity vector. Theta is the angle between them. So if you multiply the magnitudes of two vectors and multiply this product by the sine of the angle between them, remember in the first week we had defined a vector product. This is nothing but the magnitude of the vector product of these two vectors. Now, what does this vector product stands for? R cross V. What is the meaning of R cross V? We will study it in future chapter. We will see that this basically means that the angular momentum is conserved. So Kepler's second law tells us that angular momentum of planets is conserved. Now let's look at Kepler's third law. This is not the second law, this is the third law. What does it mean in terms of our current knowledge about the language that Newton invented? So Kepler's third law just relates the period and the, well, S is not actually the radius, but if you take an ellipse, there are two types of radiuses an ellipse has. If this is the center, you can imagine the longest line that goes through the ellipse and the shortest line that goes through the center of the ellipse. One is the longest line is called the major axis. Well, major means big. And the other one is the minor axis. It is the smaller axis of the ellipse. And the half of these sides, the B and A, well, B is the half of the major axis, half is semi-major axis. In the notation of your book, B is S. So the Kepler's third law just tells us that t squared, the period of the orbit, divided by the semi-major axis cubed, it is the constant, meaning it is the same for any orbit in the solar system. That is, his observations are based only on the solar system. Now, although the orbits of the planets are almost circular, are ellipse, they are almost circular. The deviation from a circle for all the planets is very small. Only Pluto has a kind of a weird orbit. Now, let's just apply this Kepler's third law to the ellipse, to the circular orbit. What can we say? So we have an object that makes a circle. Well, the sun is at the center of this circle. It goes around with the speed v. So this is the radius. Now, already Kepler's second law told us that rv times sine of theta is constant. Well, for a circular orbit, r is the same no matter on where you are on the orbit. R has the same value here, here, there, the distance from the sun. Sine of theta, well, for a circular orbit, theta is always 90 degrees. So Kepler's second law tells me that this planet, if a planet moves in a circular orbit, it should have a constant speed. So Kepler's second law tells me that planets that go around a circular orbit are actually doing uniform circular motion, the motion that we studied in our last few lectures. Okay, so that is one thing we know. We have a uniform circular motion here. Well, if we have a uniform circular motion, well, we know the acceleration is v squared over r. But let's just use the Kepler's law. Let's keep this in mind. Well, what does Kepler's law tell me? I need to express t. The time it takes to complete one full revolution is that if it makes one full revolution, the distance it covers is 2 pi r. And the speed at which it covers this distance is v. So the period is 2 pi r over v. S is nothing but r. The semi-major axis is, for a circle, is the radius. Circle is just a special ellipse in which two focal points are at the same point. So let's just substitute. We have t squared over s cubed. This is 2 pi squared r squared over v squared. This is t squared. Well, 1 over s cubed is 1 over r cubed. Kepler's observation was that this is constant. I can cancel the 2 of the r's. Well, 2 pi squared is just a constant. So v squared r. So Kepler's third law just tells us that for a circular orbit at least, v squared times r is constant. Well, it is constant in the sense that it is the same for all planets. We already know that v is constant for a given planet along its orbit. R is constant because we are studying circular motion. So v squared r is by definition constant for a single planet. But Kepler's observation is that this constant, v squared r, is the same for any planet in the solar system. This was his observation. If you take the Mars, it has a different velocity than Earth, different radius than Earth, but the v squared r for Mars is the same thing as v squared r for Earth. In that sense, this is a constant. Well, Kepler didn't have any data about that. So Kepler and Newton cannot really say anything about that. Well, let's do a magic trick here. Let me first do my magic, then you can ask it. I will just divide by r and multiply by r. Nothing changes. Why? Why did I multiply it and divide? You will see. Yes, 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 yes. I have the a. I want to put a somewhere here, because if I have the a, I multiply it with m, I get a force. So this is the force acting that should be acting on my planet, such that it will be making this uniform circular motion. We are studying that special case only, uniform. Well, we started studying circular motion, a planet with a circular orbit. Then already Kepler's second law told us that if it's making a circular motion, it has to be uniform with constant speed. So otherwise, the area covered in a fixed amount of time will not be constant along as the object moves, because you see, Kepler's second law, by telling that if you observe a planet for a fixed amount of time, the area that the radius vector sweeps is independent of where the planet was initially. That meant that RV sine theta is 0. And from this, for circular orbits, we concluded that if there is a circular orbit, then the speed has to be constant for that planet. Well, a circular orbit with constant speed is what we define as a uniform circular motion. So we are doing uniform circular motion. Then we can carry everything we know about the uniform circular motion to the planet of the orbits. We know that the acceleration is given by v squared over r, so that is why, well, I first started by studying what does the t squared over r cubed s cubed ratio imply for the velocity and the radius of my orbit. I saw that it means that v squared r is just constant. It is the same for every planet. I just divide it by r to get the acceleration. Well, I cannot just divide by r. If I divide by r, I have to multiply by r not to change anything. And then I ended up having this v squared over r, which is the acceleration of my planet. It is the only acceleration of my planet because it's making uniform circular motion. There is no tangential acceleration. Well, if my planet is accelerating, then there should be a force acting on my planet. And the force has to be mass times its acceleration. So I just multiplied everything, the left-hand side and the right-hand side, by m. So this is the force acting on my planet. It is the magnitude of the force acting on my planet. Furthermore, since it is doing a uniform circular motion, I know that this force is directed towards the center. There cannot be any other force. So my planet should be experiencing some force directed towards the center where there is the sun, such that the magnitude of that force multiplied by the distance of the planet from the sun is equal to the mass of my planet, whichever planet I'm studying, times some constant which doesn't depend on my planet or on the mass of my planet. So this constant is the same for Mars, is the same for Earth. But this m is of course different. So this already tells me that the force that my planet is experiencing should be given by some constant times the mass of Earth or mass of the planet divided by the distance of the planet from the sun. So this inverse squared law of the gravitational attraction is a consequence of the, it's a consequence of the fact that of the observation of Kepler, its third law, yes. We will come to that. No. We will come to that, don't worry. Now we will use the Newton's third law. Action-reaction forces, action-reaction pairs. So this already tells me that, at least for the orbit of the planets in the solar system, each planet should feel a force that is proportional to its mass divided by its distance from the sun squared. This is what it should feel. Now comes the big step. Well, this is the force that the planet feels. We don't know if the sun feels it or not. Well, Newton, the third law of Newton, tells us that the sun should also feel the same force. Since this is the force caused by the sun, if it is caused by the sun, of course. So he postulates that this force is caused by the sun, but that also means that sun should be also feeling a force proportional to its mass. It should also be feeling a force. Since every planet is feeling a force proportional to the planet's mass, the sun should also be feeling a force proportional to the sun's mass. So let us see. So he just says that, okay, this is for a special, at least in the case of Kepler, he could derive that each planet feels such a force, but he just postulates that if you take any two masses, they both attract each other by some gravitational force law, which goes as the inverse squared of the distance separating them, and is proportional to the mass of the object who feels the force. So from this one, he just generalizes it to any object, any mass. If I have a mass m1, if I consider a second mass m2, so this mass m1 should feel a force in this direction. Let's denote it by F12. This mass feels another force. Let's call it F21. Well, this indices here. This is the force felt by the first mass due to the second mass. This is the force felt by the second mass due to the first mass. This distance, I can define it as the distance of the first mass from the second mass, or the distance of the second mass from the first mass. It just means the same thing. Just for notational consistency, I will have these two definitions. Well, let me define two unit vectors. I will define a unit vector in this direction, r12 hat, and another unit vector in this direction, r21 hat. So these are the definitions of the vectors. I have a unit vector, r12 hat. Hat just means unit vector. 12 just means it is pointing from mass 1 towards the mass 2. And here I have r21, which just means it's pointing from mass 2 towards mass 1. F12, well, Newton's third law already tells us that F12 and F21 are related. They should be equal to minus F21. This is what we know. Action-reaction pairs. If mass 1 feels a force due to mass 2, then mass 2 should feel a force due to mass 1, equal in magnitude, opposite in direction. What else we know? We had already derived over here that F12 is the force that first mass feels. So F12 should be proportional to m1 over r12 squared. This m, in this example, this m was the mass of the planet that was feeling the force. Here F12 is the force that mass 1 is feeling. So here I have m1 divided by r12 squared. F21 has to be proportional to, now in this case it is mass 2 that is feeling the force. This should be equal to m2 over r21 squared. But we know that these two forces are related. It just tells me that F12, well, this is, since F21 and F12 are related, F12 is proportional to this one and also is proportional to this one. It is proportional to the mass 2, mass of the second one. So it just means that F12 is m1. It is proportional to the mass of the first one. It is proportional to the mass of the second one. It is inversely proportional to the square of the distance between them, and with some proportionality constant. Its direction is in the R12 direction. It points from the first mass to the second mass, and I need a proportionality constant. This is my Newton's constant. So this is the force that mass 1, the gravitational attraction that mass 1 feels, that is created by mass 2. This is the law of universal attraction. So we started with, if you just consider the historical development, we just had these uncorrelated data, numbers. From those uncorrelated numbers, Kepler just came up with some patterns in these numbers. And from those patterns in these numbers, Newton, when he was developing his dynamics, he could say that there has to be a force that the planets are experiencing. Then he just generalized it. If the planets are feeling that force, what prevents just ordinary masses to feel the same force? So he said that any mass, every mass, even you are attracting your friend just sitting next to you. There's a gravitational attraction between you. It is very small to feel. You are feeling the gravitational attraction of Venus and Mars. They're all attracting you, and there's a net force due to that. The moon is attracting you, and you are attracting moon. Yes, let's come to that one. Okay, this is nice, but I mean, if you look at in Wikipedia, you will find some number for the mass of the Earth. How do you measure the mass of the Earth? It's easy to make measurement of your own mass. Well, there are various means. If you want to be really precise, you just pick up a standard mass, and you just attach a string between you and the standard mass. When we were discussing the definition of the masses, you just let the standard mass and yourself accelerate, and then comparing the acceleration, you can find out the ratio of your mass to the standard mass. That is one way of measuring your mass, but you cannot imagine doing this for Earth. Or you can say, just take a scale, put yourself on the scale. The scale will tell you your weight, but from your weight, we know the gravitational acceleration at your position. Just divide your weight by the gravitational acceleration constant, and you will get your mass. But this is also not possible with the Earth. You cannot measure the mass of the Earth like that. But let's see, we already have one knowledge. Well, this G. So here we have a force between Earth and you, but we also have another observation. We know how objects on the surface of the Earth are moving. They move with constant acceleration. Well, one thing, this law of universal gravitational attraction tells us that the actual motion is not constant. Actual motion doesn't have a constant acceleration. As your object is going away from the center, the force will change with the distance from the center of the Earth. So as the distance from the center will change, your acceleration will change. Well, let's first write down your acceleration. So this is Earth. Let's suppose you are just flying, you are Superman and flying over there. You are flying, okay. The Superman has the mass ms. Well, there's an acceleration due to the gravitational attraction. Well, the force that Superman will feel, it will be towards the center. Its magnitude is the Newton's constant, mass of the Superman, mass of Earth, divided by the distance from the center of the Earth. Well, Newton's second law just tells me that this should be equal to the mass of the Superman times the acceleration of the Superman. Assuming that Superman is just sitting there without doing anything actively. So he's just under the influence of the gravitational attraction with some initial velocity. So this will be his acceleration. It will be towards the center of the Earth. And this acceleration will be nothing but Newton's constant, the mass of the Earth, divided by the distance of Superman from the Earth. from the center of the Earth. Remember, this r is the distance of Superman from the center of the Earth. This is my r. It is not from the surface. Well, if the Superman is, well, you are not Superman, so you are just sitting on the surface of the Earth. So the acceleration that you will feel if you just jump up, which we know that is equal to g. We know that on the close to the surface of the Earth, all the masses have the same acceleration, 9.8 meters per second squared, toward the center of the Earth. So this g will be nothing but Newton's constant, mass of the Earth, divided by the radius of the Earth squared. This is right on the surface. Well, the radius of the Earth is more or less around 6,300 kilometers. Well, intercontinental planes, they fly at 10 kilometers. Well, 10 kilometers is less than 1% of this distance. So if you are flying in 10 kilometers, the gravitational acceleration you will feel will differ from this number by less than 1%. It will be, for most equipment, it will be just negligible. So you can say that up to 10 kilometers high in the air, the gravitational acceleration from the surface up to 10 kilometers, the gravitational acceleration is just constant. It's almost constant. And this is the gravitational acceleration that we measure, which is 9.8 meters per second squared. So this is something we measure. That we know. The radius of the Earth, in one of your homeworks, you discuss how we can measure the radius of the Earth. So that you know how to do. If we want to find the mass of the Earth, we need to find this Newton's constant. So in order to measure the mass of the Earth, we need to measure Newton's constant. And we do that with what is called the Cavendish experiment. So what he did was, he basically, you just take a string, a very narrow one. You are probably familiar with this phenomenon. You take a string, a mass attached to the end. If you just rotate it in one direction, it will just swing back and forth for some time and then stop. Because the string itself is exerting a force on this mass and trying to bring it to its equilibrium point. If you take a very narrow string, attach two masses such that they balance each other, if you just leave the system for some time, then eventually the system will come to an equilibrium point. Now if you just touch one side very slowly, it will just first rotate a bit, then stop, and then come back. There is a force. Well, it just means, since its acceleration is non-zero away from this equilibrium point, it is just telling us there is a force acting on it. And this force will depend on how much you twist your string. So you can calculate that force. Then what you do is you just bring another mass from here. Well, there is a gravitational attraction. So this second mass will attract this mass. It will attract until the force due to this string balances the force due to the gravitational attraction. Now, by measuring how much this rod rotates from this equilibrium point, you can measure how much force is exerted on it. So you can measure the force, the gravitational attraction force between these two masses. Well, if you measure the force is equal to this Newton's constant, the product of the masses divided by the distance squared. This is the magnitude of the force. When it comes to equilibrium, the force exerted by this string is equal to the force of the gravitational attraction between these two masses. So you know the force, you know the masses, you can measure the distance, which gives you Newton's constant. So we can just measure Newton's constant through this experiment. But once you know this constant, in this equation, the only unknown is the mass of the Earth. So by measuring G, you can determine the mass of the Earth using your knowledge about the radius of the Earth and the Newton's constant. So in a sense, measuring G is measuring the mass of the Earth, measuring the Newton's constant. Yes, the Kepler had a constant. Kepler told us that T squared over S cubed was a constant. Again, we can do this for a circular orbit. For a circular orbit, this will be equal to 2 pi r over v squared divided by r cubed. This will be equal to 2 pi squared divided by v squared over r times r squared. This is the acceleration, 2 pi squared. The acceleration of the Earth is the Newton's force, Gn, m1, m2, or let's say m of the mass of the planet, mass of the sun, divided by r squared times r squared. Well, r squared, they just cancel. This is equal to 2 pi. Sorry, the acceleration is this one divided by the mass of the planet. So the mass of the planets, they also cancel. So we end up having 2 pi squared Gn mass of the sun. Well, we don't know this constant because we don't know the mass of the sun. But we can measure this constant. We have observations that tell us what the period of the orbit is. If you consider Earth, the period is 365 days plus 4 hours. You can determine the distance of Earth from the sun. So that gives you this S or this R. So this ratio is known for Earth. It is the same for any planet. But if you know this ratio, well, this 2 pi is just a constant. Newton's constant is a constant which we measure by Cavendish experiment. So by looking at observing that ratio T squared over S cubed for planetary motion, we can determine the mass of the sun. We don't need any scales or any strings to measure the mass of the Earth or the sun. Just observing the orbits of the planets, we can determine the mass of the sun. And by measuring the constant uniform gravitational acceleration on the surface of the Earth, we can determine the mass of the Earth. And depending on how you precisely determine these constants, will determine how precisely you know those masses. Any questions? Yes. So it depends on the sun's mass. It doesn't depend on the which planet you are studying. Which one is not universal? Well, he didn't make any claims. He just said that for any planet orbiting the sun, T squared over S cubed is a constant. He didn't know what that constant was. He might not even have guessed that that constant depends on the mass of the sun. I don't think he even knew that anything had anything to do with the mass. Okay, one question. We said that Kepler, this law of gravitation, well, we went the other way around. Starting from elliptical orbits, we can say that the gravitational laws, the gravitational attraction, should have this form. But if the gravitational attraction has that form, then the orbits have to be elliptical. This includes any kind of orbit. If I just take this chalk, throw it in the air, well, that should be an ellipse. That is in orbit. That was in orbit for a very short amount of time until it hit the surface. If it could go through the Earth, it would just be going through an elliptical orbit around the center of the sun, around the center of the Earth. Because the gravitational attraction gives us elliptical orbit, almost, let's say. Almost. Let's see. This is our planet. We are standing here and throwing a projectile. Now, if the Earth was actually a point and not this solid thing, if it became a black hole, now the force we feel at this point will not change, because the force only depends on the distance from the center and on nothing else. If we threw it with some initial velocity, what we observe is that it just makes such a motion, which is almost a parabola. If the Earth was just a point at its center, its trajectory would have been such an ellipse. Now, if you take any ellipse, the tip of the ellipse is almost a parabola. So a parabola would look like this. And you see very close to this tip, it is almost an ellipse. They are the same. An ellipse and a parabola, they are the same. It is just, if we make an experiment here and throw this chalk and the chalk just falls over there, I will not be able to distinguish an ellipse from a parabola, because there's also the air resistance, which will just destroy anything, which will cause more uncertainty in my measurements than this deviation from the ellipse. But the trajectory is, in fact, in the absence of air resistance, is just part of an ellipse, not really a parabola. But it's almost a parabola. Well, we can discuss it in the break then. We can discuss it in the break. Any questions before you leave? On Tuesday, we will just continue from where we left. Well, g is the acceleration you measure on the surface. So when you are sitting on, so hold on a bit. We have cheated a bit. There are a few points that we were not really precise enough. First of all, Newton's law of attraction is valid only for point particles. It is not valid for extended objects. So I cannot really apply this law for, let's say, for the Earth. But we will see on Tuesday that if you consider any spherical object, and if you are outside it, for Superman flying over here, this spherical Earth, the gravitational force that this Earth creates is the same thing as if all the mass of the Earth was centered at its center, was concentrated at the center. The force doesn't change as long as you are outside this sphere. It just behaves as a point mass. So if you are sitting on the surface of the Earth, you are outside this sphere, but since you are outside the sphere, the Earth as a whole will behave as if it is a point mass at its center. So the force you will feel will of course depend on your distance from the center of the Earth. That is the radius of the Earth. Now the black hole thing. Okay, on TV, on several films, what you see is you see this spaceship just flying calmly without any difficulty, and then suddenly the star on its back becomes a black hole, and it just starts sucking in the spaceship, although the position of the spaceship didn't change. So this is not physics. This is false. If sun became a black hole today, we will not feel any difference in terms of the gravitational attraction, because gravitational attraction only and only depends on the distance from the center of the sun. It doesn't depend on anything else. It doesn't depend on the properties of the sun. Whether it's a black hole or a shining sun, it doesn't make any difference in terms of this gravitational attraction that we feel at this point. Did it answer your question? In reality, yeah. Yes. In reality, whether the sun becomes a black hole or not, in terms of gravitation, doesn't affect us at all. Okay, we need to empty the classroom. So if you have any questions, we can continue discussing. See you on Tuesday.